Chebyshev's theorem or Chebyshev's rule works for any type of distribution. And so it's good if you want just a rough approximation. Now, for a lot of our data sets, we're going to be assuming that they're symmetric and bell-shaped. So something that looks like this picture right here. And when you have a distribution that looks such as this, that's symmetric and bell-shaped, we can use the empirical rule, which gives us a better approximation of how our data is spread out. So if we have a data set that is symmetric and bell-shaped, then this theorem or this rule tells us that about 68% of the data lie within one standard deviation of the mean. So if you take the mean minus one standard deviation and the mean plus one standard deviation, then right away, 68% of your data is within that range. Then there's also about 95% of the data which lies between two standard deviations of the mean. So if you go the mean minus two standard deviations, the mean plus two standard deviations, within those two numbers that you just found, there's going to be about 95% of your data there. And then lastly, about 99.7% of the data is going to lie within three standard deviations of the mean. And this will be a very important concept when we start talking about probability and normal distributions and the central limit theorem. And those are all just a bunch of words at this point, but this is very important. Get these three percentages down: 68, 95, 99.7. So up here, it's called the empirical rule, but sometimes people will refer to it as the 68, 95, 99.7 rule. And that's just signifying how important these three numbers are to essentially all of statistics. And we're going to apply it to this question down here. So in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States, ages 20 to 29, was 64.3. My recommendation with these word problems is once you get a number, write it down in symbols. So we're told the sample mean, which symbols is X bar, is equal to 64.3. And then we're told it has a sample standard deviation of 2.62 inches. So sample standard deviation is little s, which was 2.62. And now we want to estimate the percent of women whose heights are between 59.06 inches and 64.3 inches. Notice that 64.3 is our mean, and 59.06 is below the mean. So if we take our mean, 64.3, and I'll write it in symbols just so we get the practice, and we subtract off one standard deviation, as a number, we end up getting 61.68, which is not the 59.01 that we're looking for. So 59.06 is more than one standard deviation below the mean. Let's reapply that. So we're going to take 61.68 and minus 2.62. And what this amounts to is the mean minus two standard deviations. All right, so this calculation is X bar minus 2s. And once you do this calculation, you get 59.06. So we know that 59.06 is 2, I'm going to use SD for standard deviations, below the mean. And since we're going to assume that the distribution of heights are bell-shaped and symmetric, we're going to apply the empirical rule. So we know that if our distribution looks like this, here is our mean, Here is 1 standard deviation below. Here is 2 standard deviations below. Sorry about that. And so if we want to figure out how much is within this region right here, we know that 2 below and 2 above makes up about 95%. And since this thing is symmetric, if we just took a line and cut the bell right in half, half of that lands here, half of that lands here. So if 95% makes up the whole thing, then this half by itself is going to be 95 divided by 2, which gives us 47.5. So in conclusion, we can conclude that about 47.5% of women have a height between 59.06 inches and 64.3 inches.